Every day, millions of people search for short-term lodging, expecting instant results. But behind that effortless discovery sits a rigid transactional requirement. A single room on a specific date can only be booked by one person. This animated diagram illustrates the dual consistency paradox. On the left, we have a massive volume of read traffic, exploratory searches, and filtering. This side tolerates eventual consistency. It is acceptable if a search result is a few seconds out of date, because the system must serve those results in milliseconds. The right side represents the right path. When a user actually attempts to commit a reservation, the system demands strong consistency. The transaction must be absolutely correct. If the architecture fails to isolate those rights, you encounter a right skew race condition, commonly known as the double booking problem. This happens when two distributed users, perhaps continents apart, look at the exact same available room. They both click reserve, their requests travel across the network, and they attempt to claim that unique inventory at the exact same millisecond. Solving this at a global scale means you cannot rely on traditional monolithic database locks. You have to decouple your read and write paths entirely, implement atomic in-memory soft holds, and coordinate the final booking through Saga orchestration. The engineering effort to prevent that single overlapping millisecond dictates the design of every layer in a modern, event-driven microservice architecture. Let's examine how a naive, monolithic database handles a sudden spike in concurrent booking traffic. This timeline graph tracks a classic race condition. Thread A and B execute simultaneous requests. Both read the exact same availability state. One room left. Both execute an update command. The database processes both blindly. The inventory drops below 0. The room is double booked. The traditional defense mechanism is pessimistic locking. The application issues a select for update query, forcing the database to lock the row as soon as thread A reads it. However, holding a row-level lock blocks all competing connection threads until the entire transaction completes. During high-demand events, this creates a severe bottleneck, rapidly exhausting the database connection pool and taking the system offline. An alternative is optimistic concurrency control. Here, the system proceeds without locks, reading the inventory count alongside a version number. It only updates the row if the version number hasn't changed. This shifts the conflict resolution burden to the application layer. Under high contention, the version check will fail repeatedly. The application must process massive volumes of retries, resulting in high abort rates and a frustrating user experience. To maintain data integrity without explicit application locking, the optimal relational approach relies on database check constraints. We configure the database engine to enforce a mathematical rule: the inventory count cannot drop below 0. By delegating conflict resolution directly to the database engine's constraint layer, the system processes updates atomically. The first thread to commit succeeds, and the database instantly rejects any subsequent payload that violates the 0 inventory rule. The database can prevent an overallocation at the exact moment of a write, but a modern booking flow introduces a time delay. Collecting payment authorization from a third-party gateway often takes several minutes. Holding an open ACID transaction in a primary database for 3 to 5 minutes while waiting for a credit card to clear is catastrophic. It ties up critical system resources and paralyzes overall availability. To bridge the gap between reserving the inventory and processing the payment, we use an in-memory lock known as a soft hold. This sequence diagram models a Redis cache layer managing holds. A user clicks reserve, hitting Redis to secure inventory before payment. Redis uses a Lua script to execute watch and multi commands. Guaranteeing checking stock and placing the hold is one indivisible operation. That active soft hold is assigned a time-to-live countdown, typically 10 minutes. If payment fails or the cart is abandoned, the timer expires. A reconciliation mechanism detects the expired hold, dissolves the lock, and automatically routes the inventory back into the available pool. The soft hold paradigm isolates the delay of payment processing. It guarantees inventory exclusivity for the buyer during checkout, while completely protecting the transactional database from prolonged locks. A single reservation spans multiple distinct domain boundaries: an inventory service to track rooms, a booking service to record the reservation, and an external payment gateway to handle the charge. Traditional distributed transaction protocols, like two-phase commit, require all these services to lock their resources simultaneously. If one service is slow, the entire system halts. This rigid coupling fails across independent network boundaries. We solve this using the Saga pattern. A central orchestrator coordinates localized transactions, driving a state machine progression. It records a room hold locally, then sends a command to authorize payment. But if the external payment gateway rejects the charge, the orchestrator halts forward progression. It immediately triggers a compensatory transaction. This is a specific command sent back to the inventory service to actively reverse the previous local transaction and release the soft hold. To execute this safely, every command the orchestrator sends must include an API item potency key, a unique identifier tied to that specific transaction attempt. If a network timeout forces the orchestrator to retry a command, the receiving service recognizes the item potency key and does not process the request twice. This prevents edge cases like double charging a user's credit card. By designing systems to accept intermediate states and execute automated rollbacks, you achieve a level of resilience impossible when globally locking independent microservices. Once the reservation is safely committed on the right path, we must update the global discovery path. We have to keep the heavy search query load isolated from the transactional database. When the Postgres database confirms the commit, it triggers a change data capture event. It pushes a standardized event packet containing the updated inventory state onto a central message bus, like Kafka. An Elastic Search Index consumes this event, updating its availability grid asynchronously. This architectural bridge forces a specific trade-off. We accept a few milliseconds of eventual consistency in the search index in order to deliver sub-second read performance to the end user. Pairing an eventually consistent search index for exploration with an authoritative database validation at checkout creates the exact equilibrium required to handle massive global scale. This complete system map traces the entire payload journey. The user searches via Elasticsearch, locks the inventory in the Redis cache, triggers the Saga orchestrator for payment, commits the final reservation to Postgres, and updates the search index asynchronously via Kafka. The architecture serves exploratory reads instantly using horizontally scalable nodes. The primary database remains completely isolated from the noise, free to process only confirmed writes. When that final write request successfully arrives, the orchestrated state machines and strict database constraints enforce absolute correctness. Decoupled consistency regimes, atomic soft holds, and Saga orchestrators work together to completely eradicate the write skew problem. Mastering global system design requires accepting that there is no single perfect database. True scale comes from architecting fault-tolerant boundaries and precisely orchestrating state across distributed systems.